My name's Gokul, and today we're going to go through the worksheet for the fifth section for CS188. So let's go ahead and take a look at this. So this question is on MDPs, or Markov decision processes. So we have Pac-Man acting in this grid world where he can basically go north, east, south, or west, and he only gets a reward when he eats this dot over here, and he gets a reward of 1 point, and the game ends when the dot is eaten. There's a discount factor of 0.05 and no living reward, so you want to try and get there as quickly as possible. So when we think about the optimal policy for this, well, it's going to be what gets us there as quickly as possible. So it's going to be basically, taking the action that would move us most quickly towards our goal state over here, because this is the only state where we can get any reward, so we want to try and get there as quickly as possible. For A and B, we can either go, to the right or down. They'll both bring us one square closer to the goal here. So there's actually two right answers for this over here. In general, your policy is a distribution over actions, not just a single action. So you could, execute either of these with half probability, and that would, just be just as good. Um, so this question focuses a bit on, computing the values for states. So in the solution PDF for this, they'll go through how you actually run value iteration in total for this question. So I recommend you take a look at that if you're interested, but I'm going to go through how you do it a little bit more quickly. So for this question, right, we know that we can get a reward of 1 from here. And, we're starting off in the state A over here. So the question becomes, how much will we basically discount our reward before we get there? So if we count the number of hops we have from over here, we have 1 hop, 2 hop, and then 3 hops to get over here. We could also take this path over here at the same total length. So this, let's say this is hop 0, this is hop 1, and this is hop 2. The indexing here tells us how much of a discount we will have. So if it took us, just 1 hop to get over there, then we'd have, like a gamma to the 0th discount, which is equal to 1. Over here, we would have a gamma to the 1th discount, 0.5. But here we actually have, gamma squared. So we have a discount of, 1/4. And because our reward is 1, this is what we end up getting overall. So our value for this state is 1, because this is the optimal value we would get at this state if we, continued acting optimally. So then we can use something pretty similar to take a look at this question, which asks, what iteration of value iteration will get us there. So for iteration 0 value iteration, we initialize all states to have value equal to 0. And at iteration 1 of value iteration, the states next to this one, namely E and C, will start having a value that's non positive. So iteration 0, everything will be 0. Iteration 1, E and C will have a value that's non-zero. We can tell this is true because when you move to the state F, you immediately eat the dot and the game ends. So this is why the F state still would have a value of 0, because when you're there, you've already kind of used up all the value. But C and E would, after one iteration valuation, because you get a reward of 1 during the transition from C to F or E to F, would have a value that is non-zero. So on iteration 1, these two have a value that's non-zero. Iteration 2, these two have a value that's non-zero. And then on iteration 3, A would have a value that's non-zero. So k equals 3 will give us the value, the first non-zero value, which if you, count over and look at our discounting argument over here, will be the optimal value for the state. For this question though, if what I said was a little bit too quick, I recommend you take a look at the solutions. They go through the value iteration algorithm in detail, and that is basically a more formal way of doing what I just did. So now let's take a look at the next part of this question. So here, instead of doing value iteration, we're trying to do policy iteration. So in value iteration, we basically do Bellman backups. until we have, a value for every state and they're all converged. In policy iteration, instead what we do is we run value iteration with the current policy, and then we take a look at the Q values for every state action pair, which we can compute because we know the values for, once we end up in a state S prime, well, what the value will be after that. And we can basically say, okay, I'm going to update my policy to take the action that corresponds to the maximum Q value. And then we can basically do this repeatedly until the policy converges. So the first step is we initialize with some random policy. We run value iteration with this policy to give us an approximate value for each state when acting according to this policy. And then we basically improve our policy by taking a look at the Q values corresponding to every state action pair and setting our policy to do the one that has the maximum across Q values for a particular state. So this can actually converge a lot more quickly than value iteration because, let's say there's three options and, one's like 10, and then one's like negative 100, and one's like, negative 10,000. For value iteration to converge, all three of these values would need to be completely correct. But for policy iteration to converge, we just need 10 to be, stay greater than these two, which might actually be a lot easier. So let's take a look at this question over here. So this question is asking us to, first calculate the values for, when acting according to this policy, and then run one iteration of policy iteration to actually improve this. So let's take a look at how we would do this. So we basically have in this table with this pi I, the instructions for how to act in every state we will see. And we basically follow these instructions until we reach the end of the episode and record the discounted sum of rewards we would get. There's no discount here though, so we don't actually have to worry about that. The only tricky part of this is we have a living reward of -1. So let's take a look at this from state A. So from state A, we would go east. That gives us a reward of +1 for getting to the dot, and -1 because we, have a living reward of -1. So this gives us an overall total reward of 0. When we start from state C, we would, go east, which takes us to the cherry. That gives us a reward of 5, and then we would go up to B. In either case, depending, it doesn't really matter if the F cherry is there or not. And then that gives us a total value of 6. But it took us 2 steps to go here, so we have to subtract 2 because of the living reward, and that gives us a value of 4. Then if you take a look here, you're 1 away and you just go north. So similar to A, you'll end up with a value of 0 for both of these. Then over here for E, you basically go west and you kind of reduce to going over here. So you basically have one more step of this negative living reward. So you'll have a living reward of -1. 2 is 2 steps away, so you have one more -1, so you end up with a total of -2. So then the question becomes, okay, we've calculated all these values. How do we actually, improve our policy? So let's think about this. So in A, right now, if we take a look at A, our current option gives us a value of 0. But if we were to go to C instead, our value function tells us we'll get a reward of 4. And even if we have a -1 from the transition here, we still have we have a 4 over here, and -1 plus 4 is 3, and 3 is greater than 0. So we would update our action here to be going south instead, so we can get to this C state. When we take a look at E, we definitely want to go ahead and grab these cherries, so our action is probably going to say go east. And if we actually do consider all the options, we would actually see that. When we take a look at D, well, actually, one thing here we can do that's, I think, an easier case is that in F, there's only one action you can take, which is to go west, so it's going to stay west. And before we take a look at these, let's think about this one over here. So if there's no cherry at all, and f cherry is false, there would never be a reason to go to f because that will lead to a higher negative reward at a lower value, and there's no possible benefit from that. So we would definitely want to still keep going west. Instead, though, if we wanted to, if the f cherry was there, then this f state would actually have a higher value. So we'd want to actually change our policy and instead go east. We'd want to go grab the cherry and then go back here. And that'd give us a higher total reward. So this should be east. Then we can take a look at these two states. So if there's no, if this question, it's a little bit poorly worded. It should stay here. We're assuming whenever you're in state D, the D cherry is gone. Um, that's what, so that's kind of implied here, sorry, but it should be written there. So if we're here and the f cherry is false, then there's no reason for us to do anything but just go grab the dot and finish. And if we were to actually, compute all the different values and, take the argmax over them, we would see that. So this would end up being north. And, same as we had before. Instead, though, if the f cherry value is true, this, I believe, would imply that we'd want to actually go to the east. So you'd want to actually, go over a couple, grab the cherry, and then come back because you get, there's like -1, -2, -3, -4, but you get a reward of 5 for grabbing the cherry. So I think this ends up being east actually. So I think the solutions for this one end up actually being a bit wrong. So let's take a look at the second part here. So we're asking for the range of living reward values such that Pac-Man eats exactly 1 cherry when starting in position A. So let's compute the values for Pac-Man eating 0, 1, and 2 cherries. Because if we know what these three things are as a function of the living reward, then we know that, okay, we can actually then figure out, we just need to find the living reward such that, 1 is better than 0 and 1 is better than 2. So if Pac-Man just goes to the goal here, he gets 1 for getting the dot plus X, where X is like the living reward. If instead Pac-Man goes and grabs these cherries, he gets 6 points, but he has to get 3 times the living reward. So we get 6 plus 3X. Similarly, if we do it out for 2, we will get 11 for grabbing both cherries and the dot plus 7X. And then what we want is basically something such that, considering all 3 of these inequalities, we want this one. So we want 6 plus 3x to be greater than x plus 1. So we definitely grab, 1 cherry over 0. But we also want it to be greater than 11 plus 7x because we don't want it to grab 2 cherries. We say exactly 1 cherry. So if we actually solve out the system of equations, you should get something that says that we want x to be, negative 2.5 is the lowest value we'd be okay with, or that kind of be the cutoff point. And the highest value we'd be okay with is negative 1.25. And if x is basically, inside the range defined by these two values, then it'll be most advantageous to just get exactly 1 cherry. So that was question 1.